copy of that model paper. That'll help you out. You can do that in the graphics.
And you want to use this for separation of what? Okay, we're shooting now.
After that, we will separate it by this one.
Now this, you know, right now you're separating. That's suffix.
Yeah.
Okay. And this come in. Yeah. That's the second fraction.
Yeah.
Now the crystal that we have here is this is the what? The astronomy, the aldehyde, right? And then the crystal. Good. Now this is the portion of this portion, right? This compound, right?
Yeah.
Now these compounds, it seems that they are very pretty, aren't they?
Yeah. Very pretty crystal.
And then we're going to send these for Eli Lilly.
Eli
Right?
Lilly.
So these are the
Example.
how many milligrams we have here?
Yeah, maybe 20 milligrams.
These are pretty colored. Now you told me.
This is their
this is all the
Yeah.
products. And then we have here these crystals. Oh.
Yeah, very pretty.
Pretty crystals. All these are nice also. Okay. So all these compounds, how many of these samples we have sent to Eli Lilly? We have sent about what, 28 compounds?
Yeah, 28. Totally 28.
Okay. Now right now we are waiting for the results to come from Eli Lilly, from Dr. Merriman's. Okay,
Yeah.
that's good. This is what?
This is the
compound.
product.
Oh, that's the byproduct of the. Okay. Oh, that's very good.
Yeah.
Okay. These are very good, and it seems that they are very pure
Yeah.
crystals.
Spectrum identification.
Yeah, very good. So. What? This is the acid that we
Yeah.
have right
Yeah.
now.
Yeah.
And that's good. That's the NMR, and
Yeah.
it has. This is for the.
Acid.
This peak is for the COH,
Right.
and then we have all of the, and also this is the benzyl derivative. This is starting compound,
Look at that.
and
This
and
shape
that's
is
right. Now
very
we have
clear.
the okay. Then you take the starting compound and
got the acid.
okay, and you hydrogenate and you get the acid. Now how did you?
And then nobody report this one, right?
Right. This one.
This acid.
Uh-huh.
Yeah, now the TLC is pure
Uh-huh.
and the NMR pure. Now we will know the MS spectrum.
And you know what the yield is?
Oh, the yield is good, about 80%.
About 80%. That's very good.
Yeah. Oh, the student take it.
You have another one? This is my charcoal. Let me go on the video. Ooh, that's impressive. Yeah, that's a nice machine. Yeah.
What does it allow you to do?
It is, you take the compound and it's sort of, you take, in a way, you take the source and then you get this piece. The that's correct. Yeah.
All right.
And so each one of those, let's say, each one of those absorption of the peaks that you have, that indicates a certain structure, a certain part of the molecule. And then you put that the different structures together like a jigsaw puzzle, and then you find out what it is. When you want to identify a compound, you have, let's say, you take different, physical, measure the different usually you take, let's say, probably you take the volume of the compound, okay? And then you go and take the, with what function you have to have certain area. So guaranteeing that area, you say that the compound must have certain function, right? And in the same way with this type of spectrum, and because you have gas and then depending where those absorptions in the chart come,
Sure.
I have this type of hydrogen.
Dr. Behforouz, should I edit the pressure?
The what?
Should I edit the hydrogen?
No,
No.
just
Look
yeah,
like,
right,
okay.
Right. Yeah, you want to put that.
So it's doing what you're doing.
This is actually this part is like that. Well,
Okay, that's good. Hey,
Okay.
Maybe that's a big magnet. Tim.
Big magnet will take care of it.
Yeah.
I know.
That's okay. You
You
go
do
ahead.
that.
You want me to do it?
Yeah, you do that.
Okay. Let's go ahead. We'll have DMSO. Is that DMSO?
yeah.
Fine, if I do. Don't stop.
Yeah.
Any
Yeah.
product in it, huh?
Yeah, this DMSO.
Okay. So what do we have? And then we have USB. EF4. Okay. The metal group that we have,
Uh-huh.
and that's the water,
A
the
little
OH.
water, yeah.
Okay.
Okay.
How long has she been working with you?
Oh, one guy.
One time.
All time, no.
You ready now?
Right.
Go right ahead.
Okay.
So you were going to ask
Can I
me
ask you-
question?
Yeah.
Okay.
Amazing. Tell me about the research from the beginning. How did you happen into
Yes.
this study?
Yes. Since I joined Ball State in 1982, one of the research projects that I was interested was to prepare a compound which is called levendomycin. And levendomycin is a natural product which was isolated from the fermentation broth of a bacteria, one of the bacterial species of the Streptomyces strain, which is called Streptomyces lavenduli. And this bacteria is a salt bacteria, and generally they can isolate the salt bacteria, and then the culture of the cell bacteria, the culture of these bacteria from the fermentation broth of the culture, then they can isolate compounds, that sometimes these compounds are antibiotic. And this levendomycin was an anti-cancer agent, but the problem with the levendomycin itself is that it is actually toxic more toward the normal or body cells compared to the cancer cells. What we were interested to see whether we can synthesize this compound and probably do some more studies and find out how active it was and toward the cancer. Now, since 1982, there has been two synthesis or two preparation of this compound, but these two preparations, one was done by a group in University of Rochester, and another one by a group of chemists at Purdue University. But these two syntheses, these two preparations, are very long and involve many steps. So we tried to see whether we can synthesize the compound or prepare this compound in shorter steps. Fortunately, we were able to prepare the compound in 5 steps, and while the other two groups, they could prepare the compound in yields of less than 1% and many steps, we could prepare it in 5 steps and also an overall yield of about 40% yield. Now, during the preparation of the compound, one of the intermediates which was involved prior to the final step of the levendomycin methyl ester, this intermediate, when we did the screening tests for the anti-tumor or anti-cancer studies in collaboration with our friends at Eli Lilly and Company, we found out that this intermediate was quite active, and also it was selective toxic. In other words, it was killing the cancer cells compared to the normal cell. It was killing the cancer cell much more efficiently. And then from then on, what we did, we made several analogs, and we did some tests on these analogs. And among these analogs that we have, there is one analog that has a selective toxicity of 130. In other words, it kills the cancer cell 130 times more than the normal cells. Now, you know that generally when you want to find a drug, you want to have a compound which is selective toxic. It will kill the disease cells or it will kill the bacteria and not bother the normal cells. And so this compound seems to be quite selective, as I mentioned. And we did, or Eli Lilly researchers or friends at Eli Lilly, mainly the Dr. Merriman's group at Eli Lilly, they did the animal, the testing in the animal system as well as in the tissue cultures, which they call in vitro testing, as well as in the animal testing. And they found that this compound is actually quite selective, and even in animals there is no toxicity in animals, and generally the animal not even losing any weight, even when these compounds are introduced, and they reduce the tumor size of the cancer tumor size in the mice. That's the animal that we tested on, by about 90%, which is very good, and without the animal losing any weight. So what we have done, we have tried to make more of these compounds, more of these analogs, and especially find some compounds that they are more soluble in, let's say, in a system like water, aqueous solution or water solution, and try to see whether we can find even more active and more soluble compounds so we can then, use them as potential drugs. The compound, the interesting part of these, or the activity of these compounds, is that the compounds are active against cancer cells. That these cancer cells, they are associated with the let's say cancers such as colon cancers and breast cancer, and also the pancreatic, or the cancer of pancreas, for which right now we don't have any effective drugs. So if this project, let's say, succeed, and if let's say we have a drug, then it will be good actually for the treatment of these tumors, for which we don't have any drugs right now. Now we have a patent application that has been filed with the U.S. Patent Office, and the patent belongs to Ball State, but the Eli Lilly has we have quite a bit of support from Eli Lilly, and Eli Lilly has the exclusive right to produce these compounds if they become drugs. And at the same time, Eli Lilly had to spend several $100,000, which I'm grateful to what this company had done, and also their researchers. And I think that this is what it should be as far as a collaboration between industry and university in order to find better cures, better medicine, or even train students to go to these companies and do their job. And also, I have had support from the National Institute of Health, the Cancer Institute, as well as support from the Delaware County Cancer Society, as well as I had support from the Ball State University Research Office of Research, and of course the chemistry department, the honors college, and also I have had some support from the American Chemical Society, the Petroleum Research Fund, Research Corporation. So I have had a number of grants coming from these different sources to support the work. So this is right now what we are doing. We are trying to do to continue this work. And right now, Eli Lilly, our friend at Eli Lilly, Dr. Merriman, has about 20 compounds, 20 analogs that he is doing the screening test in the cell culture against let's say the cancer cells, and to see whether that we may have some more candidates effective against the drugs. And later on, if we find that some